Okay, let's talk about electrons and energy. So, the formula that we will use to calculate the energy of an electron. So, these electrons, we're calculating the energy that is emitted from waves. And the formula that we use for that is E for energy equals a letter H times frequency. So E here stands for energy. Energy is going to be in a unit called joules, Joules, and it's a capital J. H is a constant called Planck's constant. And Planck's constant is 6.626 times 10 to the negative 34th joules per second. And then the last variable in the equation is frequency. So remember, frequency has a unit of 1/seconds. So we have joules, joules per second, and 1/second. So this times the joules per second times 1/second is going to give us joules. So this is to calculate the amount of energy of a wave. So oftentimes the question will read, what is the energy of light, or what is the energy of the wave? So let's look at an example. So we'll say, what is the energy of light? Having a frequency of 4.41 times 10 to the 14th 1/seconds. I'm going to change that. Let's say, what is the energy of light having a frequency of 5.25 times 10 to the 14th 1/seconds. Let's do a different one. What is the energy of light having a frequency of 5.25 times 10 to the 14th 1/seconds? So we're solving for energy. We know Planck's constant that we'll be using. It's always 6.626 times 10 to the negative 34th joules per second. And the frequency that we've been given is 5.25 times 10 to the 14th 1/seconds. So we're solving for energy in joules. So I'm going to say energy equals Planck's constant times the frequency So let's do that in our calculator. Let's say 6.626 times 10 to the negative 34th times 5.25 times 10 to the 14th. So this gives me an energy of, with three significant figures, 3.48 times 10 to the negative 19th joules. That's how much energy that light having that frequency has. So this is a very small amount of energy. So another way that you might see these problems worded is it might say, what is the energy of light that has a wavelength of a certain amount? Well, there's no way to go directly from wavelength to energy, but what we are going to do is we'll use the relationship between frequency and speed of light to solve for frequency if we're given wavelength, and then plug that in to solve for energy. So if you're given frequency, you can always solve for energy using this equation directly. If you're given wavelength instead of frequency, you just have to do one more step. So let's say, what is the energy of, let's look at the visible spectrum here. It looks like red light has a visible spectrum somewhere around 700 nanometers. So let's say 700 nanometers. What is the energy of red light having a wavelength of 700, I'm going to put a decimal place here just for significant figures, 700 nanometers. What is the energy of red light having a wavelength of 700 nanometers? So we're solving for energy of a wave. So we know the equation that we need to use is energy equals Planck's constant times the frequency, but we're not given the frequency, we're given the wavelength. So first thing we're going to have to do is we're going to have to use the wavelength to solve for frequency. And then we can use the frequency to solve for energy. So there's just one more step, because we can always solve for the frequency if we're given the wavelength, because we know the speed of light equals the wavelength times the frequency. So that's what I'm going to do first. So if I'm solving for frequency, frequency equals the speed of light divided by the wavelength. So I'll say frequency equals 2.998 times 10 to the 8th meters per second. That's the speed of light, constant. It'll always be given to you. You do not have to memorize it. Divided by the wavelength, 700 with a decimal place there. Oopsie, nanometers. That's not going to work. First, we need to convert wavelength in nanometers to meters. So there's one step even before here. Convert nanometers to meters. So let's just do that up here. 700 nanometers converted to meters. There's 1 times 10 to the 9th nanometers in 1 meter. So 700 divided by 1 times 10 to the 9th is 7 times 10 to the negative 7th, but it still needs 3 significant figures. So I'm going to say 7.00 times 10 to the negative 7th meters. So that's now my wavelength in meters. If we used nanometers, we would get the wrong answer because these units wouldn't cancel. So now I'm going to say 2.998 times 10 to the 8th divided by 7 times 10 to the negative 7th gives me 4.28 times 10 to the 14th 1 over seconds. Okay, so that's the first step. It's the second part of the first step. First, we needed to convert nanometers to meters. Then we used the wavelength in meters to solve for frequency. It's 4.28 times 10 to the negative 14th. Now we can just plug the frequency in here to solve for energy. Energy equals Planck's constant, 6.626 times 10 to the negative 34th joules per second times the frequency that we just solved for, 4.28 times 10 to the 14th, 1 over seconds. And we'll get energy equals, so let's say 6.626 times 10 to the negative 34th times 4.28 times 10 to the 14th, 1/seconds. And we get an energy of 2.84 times 10 to the negative 19th joules. So for all of the math that we're going to be doing in this class, there's always 3 parts. The first, most important, most heavily weighted part of a correct problem is going to be the math itself, that the number is correct. 2.84 times 10 to the negative 19th. That's worth the most points, that you get the math right. Next is that you have the correct unit. And last is that you have the correct number of significant figures. This number, 700 with a decimal point at the end, has 3 significant figures. That decimal place makes these 2 zeros significant. So now my answer needs to have 3 significant figures. So the right math, the right unit, the right number of significant figures, all 3 of those are important to have a completely correct answer.